Our third panel, titled Next-Generation Microelectronics for Large-Scale AI Systems, will be moderated by John VerWey, East Asia National Security Advisor at the Pacific Northwest National Laboratory. Please welcome our speakers. John Shalf, Department Head of Computer Science at Lawrence Berkeley National Laboratory. Dr. Jeffrey Shainline, co-founder and CEO of Great Sky, and Dr. May Casterline, Principal Solutions Architect at NVIDIA.
All right, great. Thank you all for joining me. With that introduction, I thought we'd start by just having everyone describe their background and interests before we dive into the panel itself. So could we start with you, John?
Sure. So I'm department head for computer science. Like they said, my interests are in computer architecture, advanced packaging technologies, and I'm also interested in atoms to architecture research to find CMOS replacement technologies.
Thanks, John. May, please.
So I'm May Casterline. I'm on NVIDIA's federal team. I'm a director of solution architecture there, so I help run a team of engineers that spend a lot of time interfacing with government, the industrial base that supports the public sector community, and work on sort of strategic initiatives for NVIDIA in the space.
Wonderful. Jeff.
I'm Jeff Shainline. I was a physicist at NIST for about 12 years, where my team and I developed sort of a new way to implement hardware for artificial intelligence, and just a few months ago spun that out into a company called Great Sky. So we're trying to rebuild AI from first principles, leveraging superconducting electronics for computation with integrated photonics for communication to overcome some fundamental scaling bottlenecks.
Great, thank you. So the focus of this panel is next-gen microelectronics for large-scale AI. And John, you've written extensively about sort of the slowing down, the end of Moore's Law, what's coming. And I thought maybe I'd start with you to level set what the next steps look like. And in some of your previous writing, you've identified 3 potential trajectories. And they are more efficient architectures and packaging, new models of computation, and new materials and devices. Could you just talk briefly a little bit about that, especially now that we're in sort of this post-exascale world?
Sure. So we have to be, it's very tricky explaining, the slowdown of Moore's Law. First off, it is a techno-economic model, and we are still able to shrink transistors, with EUV and stuff. The problem is that we're shrinking the transistors. They actually get better as you shrink them, but the wires don't. The intrinsic resistance of the wire increases when you shrink it, and that's the real problem. Is in fact the data movement, not the transistors, are the biggest contributor to the energy inefficiency. And so we're seeing things. GPUs, the A100 was 350 watts max, 700 for the H100. It's going to be 1200 or so for the B100. That's why we're on that trajectory at a time when there's an insatiable appetite for AI hardware. So in the short term, we're going to do architecture specialization, advanced packaging is something that we know how to do today, and we're going to continue to turn that crank, things like tensor processors, things like that. But in the other dimension, fortunately there's lots of different dimensions to solving this problem. The other dimension is CMOS replacement technologies, or even CMOS plus X. It's probably not going to replace it right away. And that requires new materials, new manufacturing technologies, and that's where we're looking at co-design frameworks to accelerate that process, because we know today that it's typically 10 years going from lab to fab, based on looking at the FinFET and the trajectory of other technologies. We need to accelerate that process. But we don't have an obvious replacement for CMOS, so we're already 10 years too late if it's 10 years from lab to fab. So that is something also a place for investment. And then, of course, we have the third dimension, which is new models for computation, the reversible computing, quantum, neuromorphic. But those aren't necessarily replacement technologies. They're not competing against each other. They're expanding computation into new areas where digital isn't that great. And so, I think others reemphasize this. It enables new opportunities, but it doesn't solve our current power crisis in digital and microelectronics.
Thanks, John. May, NVIDIA has, of course, been doing quite a bit of work in GPU-based applications for AI accelerators. With this sort of slowdown that we're observing in the CMOS paradigm and the rise of these accelerators, how do you see the role of GPUs sort of evolving to serve needs going forward?
So I need to do a disclaimer, which I told the panel before we started this. I'm an applied AI sort of person, right? So I'm not down at the chip level. So full disclosure, I'm expertise in the area, but still have a perspective, I suppose, because I'm a practitioner. My team uses the hardware we build, and we get asked to solve increasingly harder problems and do it with hardware and software. So I think the sort of direction you can see from NVIDIA, and this is manifesting in our products, is it's not just about the GPU and the chip. I know there's a lot of focus on that as this, and it is sort of a fundamental unit that is required for the system, but system in my brain is the key word. These are complex systems that are GPUs, CPUs, memory, networking, cooling, right? So it's this complex machine that's actually accomplishing the task, not one single chip. So obviously NVIDIA spends a lot of time innovating in the chip. We are cranking out new innovations at an incredible rate. And sometimes it's hard for even us to catch up. But you'll also find if you kind of track what we can do, we'll tape out a chip, we'll package it, it'll get into the market, and then software plays a role. And so we spend, we'll cut an initial, cut of the software and that ships, and then engineering spends a lot of time finding efficiencies in the hardware and implementing them in low-level software. And so NVIDIA actually employs way more software engineers than we do hardware engineers. And so I think that is the style of innovation you're going to see come from NVIDIA into the future. More of a platform-based approach to tackling these problems.
Great, thanks for that. And Jeff, Great Sky is pursuing something similar in terms of finding algorithmic efficiencies in novel compute architectures. Could you talk a little bit more about the challenges you're targeting?
Yeah, absolutely. John mentioned a lot of the bottlenecks are coming from data movement. That speaks to our thesis, really, which is that AI is built on neural networks and different things that process information in a certain way. And if you want to do that efficiently, the best thing to do is build those computational primitives at the circuit level. So build little neurons that have their own activation functions. That's what we're trying to do. And after studying this for quite some time, I think that the best circuits for implementing these computational primitives are based on superconducting electronics. So our fabrication process, it doesn't throw away semiconductors. That's your first layer. You do superconducting electronics on top of that. And another thing we observe in existing AI is that getting data across longer distances is crucially important. And so that's best accomplished with light. Semiconductors, superconductors, and photonics. That allows you to co-locate memory with processing. That's what you can do with the superconducting layer. That means that you don't have to move nearly as much information because you're not always computing in your processor, writing to memory, reading from memory. You get rid of that a huge amount of data movement. Then when you do need to move it, do it with light. You use superconducting electronics. That means you have single photon detectors. You can now communicate at the physically lowest possible energy level for one of these communication events. So it's really about data movement, building new hardware that efficiently implements the kinds of computations that underpin AI. Those are the technical challenges we're taking on.
And building on that, John, when you think about sort of next generation large-scale AI systems, what are some of the research gaps that you've been tracking through the last 5 to 10 year period in the microelectronics space writ large?
Yeah, I mean, if we talk about the conventional computing, we've kind of gotten out of the habit of understanding how to create specialized architectures. For years, we had like this piece with MPI and general purpose CPUs. We got kind of taken off guard by the emergence of GPUs as a general computing device, and it took us a while to recover. We had a whole exascale computing project to try to turn that around. And I think that we need to accelerate our ability, lower the costs, accelerate our ability to create those specialized architectures in the interim, not just because I think it's the future, but it's also that workforce development for an industry that needs people who are very experienced with that. But when it comes to, I think the really big breakthroughs are things like what Jeff's doing, where we have new material systems combined with the CMOS, the semiconductor technologies. And there's a lot of really interesting approaches to reducing the cost of data movement. You know, photonics is great, the superconducting is great. There's also ferroelectric spintronic type things. In order to advance those devices, though, it's scale bridging. Right now, the people who do material science work in their own lane. The device people, they make one device. They say it consumed an attajoule, and well, that's great. Can you build an AND gate? No, it's too many devices. And so this scale bridging is a big framework that we need to invent. The research community needs to invent. We need to invest in that. Because just even getting material scientists to talk productively to a device person or an architect, that alone takes years of effort. We joke about how many sentences before a material scientist will bring up Hamiltonians. And just getting over that language gap is a huge endeavor, and I think that's the atoms to architecture co-design is really important aspect.
Yeah, great. May, thinking similarly about sort of gaps and opportunities more on the application level, you've of course done quite a bit of work on defense applications for AI, and we heard earlier today that there's obviously room for more integration in that space. Could you speak a little bit about sort of the most promising applications you see for national security?
Yeah, so there's buckets of promise. Obviously, there's been a bit of discussion about legacy systems, and anybody that's in the national security sort of world has to fight those systems. So there's sort of the basic applications and promise around you could just make your jobs probably easier. There's a lot of just route I'm not speaking correctly. Automation that's definitely possible with things like Gen AI, and those will quickly become somewhat commoditized. Chatbots will explode and everybody's jobs will get easier. You're seeing this in the commercial space with Copilot and things like that. And that's great, and it's, so there's that. But then there's this, I spend a lot of time in the autonomy space, in physical AI, and educating a lot in the government side around what's actually required to accomplish something like that. And to me, that's sort of where the biggest promise is in the defense space, and like I said, where I spend a lot of my time. The way NVIDIA sort of approaches autonomy, and you can see this play out in other markets, whether it's autonomous vehicles, factory robots, healthcare, surgical robots, anywhere you have somewhere where you're taking AI and putting it into some sort of physical robot that has to go interact with the 3D world and do stuff, that usually requires three main computers. Edge, that's the robot. Training, that's a lot of this big infrastructure we're talking about, facilitating the creation of all these perception models and reasoning models. And then simulation. And simulation is one of the most fascinating places I think AI will really prove dividends for the defense space. Because you have to be able to simulate the environments that your robots are going to work in. And you have to do that many, many, many times. Because defense applications are notoriously riddled with rare edge cases and a lot of lack of information as to what might happen. And so there has to be a lot of sort of informed creativity around the possible outcomes. And that is a really fascinating intersection of simulation and generative AI that we're seeing play out in the robotics space. It's very bleeding edge, and it's just starting to show up in foundation models and things like that. But those three computers are really required to sustainably, reliably, and sort of defendably, I think, be able to say, I believe this thing will work the way I want it to. Those three computers are required to do that and to be able to test and evaluate your system. So those are kind of the spaces I've been focused on a lot lately. And that, like I said, the Gen AI sim intersection and AI sort of exploring that space is where I see it going.
Fantastic. And Jeff, from a startup perspective, thinking again about challenges and opportunities as we're pursuing sort of next-gen things, obviously there's been a lot written about the breakdown between lab to fab transitions. DARPA MTO has publicly estimated that first working silicon for a startup can cost up to $20 million in funding. And of course, a lot of that is contingent on having a foundry willing to ultimately do the work. Could you talk a little bit more about what it looks like on your roadmap as you go from design to fabrication and the costs and challenges you see on the way?
Yes, absolutely. Very important question. So as I mentioned at the beginning, I was at NIST for 12 years. During that time, we developed a fabrication process in the NIST clean room, which is an excellent facility, not a state-of-the-art facility. And there we were able to show that we can integrate semiconductors with superconductors and photonics. We're doing it at a 3-inch wafer scale, state-of-the-art circa 1982. And so transitioning that, there's no steps in that process that are particularly novel. It's just not what most foundries usually do. So what we need is a foundry that can take a 45 nanometer CMOS process. Again, still not state of the art. That's, circa 2008. You run a standard 45 nanometer CMOS process and then run a standard superconducting electronics process on top of that. You don't have really small feature sizes. Cost can stay low. Nothing on our technology roadmap ever requires extreme UV lithography. So we could have tons of inexpensive 45 nanometer nodes on US soil manufacturing our hardware. But how do you get, you said the number $20 million to cut your first silicon. That's painful when you're a startup trying to just prove the worth of your technology, especially when your technology depends on innovating on the hardware level because there's risk there. And so that's what we would love to see more partnership, maybe with the federal government, say, okay, we heard it from Whitney Mason at MTO this morning. There is an appetite for DARPA funding superconducting electronics for novel compute. Great, let's go. I would love to talk more about that. But being willing to take some risks on new hardware or new hardware combinations, maybe this has been proven and this has been proven, but can you put them together? Can you handle those interfaces? Can you do it monolithically to keep your costs low? Can you manufacture in volume? How does the sort of technology to business transition take place? Those are all conversations that need to be taking place from national labs, private industry, and the government to sort of make that a navigable transition.
And kind of on that note, John, I know you were involved in the Exascale Compute Initiative, and now we have Frontier at Oak Ridge, we have LCAP at Livermore. What role do you see some of those national lab assets playing in this next generation microelectronics pursuit?
Yeah, so I think there's two kinds of scale up, and Jeff was talking about one, which is the lab to fab transition, and there's a lot of investment in pilot lines and prototyping capabilities that I'm really excited about with the CHIPS Act. But the other is the development of a virtual prototyping capability as well. And this is being able to do fundamental bulk material calculations to predict the behaviors of electronic or microelectronics materials before you even create them. The ability to do device scale simulations before you actually fab the device, and be able to do scaled up architectural simulation of a bunch of those devices working as ensembles. That is more about forming multidisciplinary teams that are working together and doing that scale bridging. We have fantastic tools for each of those different scales, and codes that run on those supercomputers are developed through the Exascale Computing Project. But the difficult task is linking those things together and also forming those multidisciplinary teams. And that's the next big thing. I think the DOE's MSRC program is trying to create that capability that spans all of the laboratories and is able to put those supercomputers, the exascale computers, to productive use in accelerating the design cycle.
Great, thank you. Yeah, May, one thing that I think we would love to hear a little bit more is there's tremendous interest on the government side to see more partnership with industry. Obviously, industry, as we've heard this morning and we'll hear more today, is really leading in the microelectronics space in a way that is not historically precedented. What sort of things does NVIDIA look for when assessing sort of ideal government partnerships? Does it come down to how the IP is treated, or what sort of are the priorities?
So we're kind of unique in the federal space, I would say. We're not pursuing direct government contracts and relationships that way. So, but it's not that we don't want to work with the government, we work with them constantly. So partnership, I think, for us from the government side is just willingness to work with, talk with us, and we will help you. We spend a lot of time advising, and I try to make the government folks that I engage with that are want help, make them as educated a buyer as possible. Because we actually, everything NVIDIA ends up making at the end of the day is for somebody that writes code. So if you don't write code, it's really hard for you to consume direct from NVIDIA what we build. So the government tends to not be the people that write all of the code. It's not that there aren't developers in the government, there is, but largely the government is incentivized legally and both financially to buy from industry, whether it's the defense base or the commercial side. And so those are really the folks we directly work with, because we build the platform. We don't really have a lot of interest in owning the end use case. We build a platform that enables many, many different industries. And so we spend our time sort of in the technical trenches with the industry partners that would deliver a solution. And then our engagement with government is more of a collaborative advising role is what I usually seek out to, again, make sure they understand the technology they're asking for, what they should look for, and how they're going to be able to solve their problem with what's out there today.
Great, thank you. So Jeff, I'd love to get your perspective briefly on sort of the transition from working in a government lab setting to now pursuing something more in industry. And I thought there were some good insights earlier this morning to that effect as well. Could you just talk a little bit about what you're seeing more from the private sector side, having now left government?
Yeah, from the private sector side, it's extremely exciting. I'm having a great time right now. So I guess when I was in the government, one of the things, I was at NIST, it's a metrology institute, we're in charge of standards, so I always had this push to be using the same circuit components to be performing high precision measurements, which makes perfect sense, that's the mission. It's now very energizing to be able to focus on my passion area, which is advanced computing, and using the right circuit elements to perform the computations that your AI model needs. And so I've been kind of liberated to put all of my thought into that. And what I find as I go out and I speak to investors, I talk to other, other startups in the space, there's a ton of excitement around this. There's a ton of interest in appreciating where AI is right now and all the incredible progress that's been made, not least from NVIDIA, of course, leading the charge there, but also excitement around new things we can do. And what if we go beyond that? What if we think from first principles about how to build this from the ground up? And then what do you find? And it's not about replacing GPUs. It's about augmenting them with special purpose machines that can solve certain problems 1,000,000 times faster because it's tailored to that. Investors like that story, and why wouldn't they? I mean, it's something where there's a ton of value to be added from coming at it focused on solving a certain problem and bringing that sort of really targeted teamwork to deliver value in one specific high-value area.
Great, thank you. John, going back to you, you mentioned some focus on advanced packaging. Obviously, this is one area where we're trying to optimize to squeeze more performance out of the compute we have on these chips, especially in the AI context. Could you talk a little bit about sort of the technical hurdles you see? What is being pursued by places like DARPA through the Electronics Resurgence Initiative and also in the ME Commons, which I think we'll hear more about later? And what, if there are gaps in the research agenda, what you think should be prioritized?
Well, I mean, with the recent investments, boy, that's a big enchilada. I mean, one of the challenges there is tooling. So we want to choose a solution and then build a packaging facility around it. And there are too many solutions, potential solutions right now. Too many substrates even. And we're already using silicon, but it's a very expensive substrate. There's a lot of interest in these classes. Again, I think there needs to be a lot of work done in fundamental materials discovery and in actually creating those materials, but even creating the manufacturer tooling. If you choose, once you choose your substrate, you might have completely different tooling in order to put that package to work. So I think this is a big ticket item, and I think Deirdre Hanford might talk some about that too. It's crucially important to paved the path for the manufacturing scale-up, but we're really hung up right now on how do you actually show which path is going to be the most promising, and that's going to be the next 5 years of the advanced packaging.
So you think the ecosystem just needs a little bit more time to mature and then standardize around a certain subset of approaches?
No, I think we do need prototypes. It's not just maturation, it's finding out if it works or not. Stuff looks great on paper, and this may be computational modeling. We need to improve our capabilities there, or we need to be more agile inside of our labs in terms of our ability to machine, pattern different materials. And so patterning science is, we've been very focused on EUV. This intermediate packaging capability that is with obsolete technology rules like 45 nanometer, we're still operating three-inch wafers in order to test those things out when all the automation, all the manufacturing equipment is based on 300 millimeter wafers.
Yeah, great, thanks, John. We've got about a minute left, so I'll go to our lightning round, May, which is going back to your comments on sort of AI for defense applications. If you could change one thing about sort of how the government is currently approaching AI adoption in the defense space, or one big blocker that you've observed, could you just talk a little bit about what that would be and how it could be overcome?
I mean, I would like to see them play offense a little bit more. I think that's it. Like, we're very busy being defensive, but offense to me is an equally valid strategy, and I would like to see us get in the game. I don't really see that in the investments defense is making, at least in a informed manner. They're focused on some parts of the problem, but I don't see large architectures being mapped out across the defense orgs and concepts of how they will actually implement them. So I would say playing offense would be great.
Great. And Jeff, last question. We're going to have an investment panel later today, and I wonder if you could talk just briefly about what you think is the most important thing for the investment ecosystem to do in support of hardware startups. We hear a lot about the need for large amounts of patient capital. What else is not on the agenda that should be?
Maybe getting to know specific companies, get to know us, understand our reasoning, dive deep with us technically to understand how the hardware layer can add value all the way at the application layer so that you can make informed bets, not just buzzwords. And I'm not saying that's what happens. There is a fair amount of this already, but really understand how an investor can work with a startup to go all the way from conception of an idea up to really adding value at the application layer.
Wonderful. Please join me in thanking our panelists.